All right, so I had somebody ask me about a question with vectors, and we're using the scalar product here. And so I just want to remind everybody of our definition of the scalar product is that if you do A dot B, you're going to get magnitude A, magnitude B, cosine of theta, and theta is the angle in between those two vectors. So we're given a problem here. So we're given that the magnitude of A is 2 and that the magnitude of B is the square root of 5. And we're also given that A minus 2B and 2A plus B are perpendicular. So we want to use that information to try to find the angle between the original vectors A and B. So if two things are perpendicular, then that means that the angle between them has to be 90 degrees. So what I know then is that if I do A minus 2B dot 2A plus B, that's got to be equal to magnitude A minus 2B, magnitude 2A plus B, cosine of 90 degrees. You'll be able to shortcut this as we go throughout the unit because the cosine of 90 degrees is 0. And so this is a really big takeaway is that the the dot product equals 0 when two vectors are perpendicular. So that's a really good thing. If you ever hear the word perpendicular, you should think, oh, dot product's going to equal 0. That's a really key concept that's going to come in when we look at like equations of planes and lots of other things. So anyway, I just wanted to show you why rather than just stating it. This is because the cosine of 90 degrees is 0. So what I know is a minus 2b dot 2a plus b is equal to 0. So then let's see, do we know if these are two-dimensional or three-dimensional here? I don't think we know. Okay, but we know that a minus 2b dotted with 2a plus b is going to equal 0. So what I'm going to do is let's just write it out as, let's see, well, we're going to look back at our different uh, properties here. So there's a couple different properties of the scalar product, and one of them is that you can distribute. So what I mean by that is if we did A dotted with B plus C, you can do A dotted with B plus A dotted with C. So I'm going to use that idea here, and I'm going to use that idea twice to distribute this like we would expect it to be. So what I mean is I can take this first chunk and distribute it here and here, resulting in A minus 2B dotted with 2A plus A minus 2B dotted with B. That's going to equal 0. And then the other one of the other properties of the scalar product is that it is commutative, meaning A dot B is equal to B dot A. So if I could distribute from left to right, then I can also distribute from right to left. So it's basically uh, just the regular distributive property on numbers, the FOIL process that you've done 100 times, more than 100 times here. So we have A dotted with 2A minus 2b dotted with 2a plus a dotted with b minus 2b dotted with b. Okay. Now another property of the dot product is that if you do, I didn't draw a big enough box, if you do any scalar times the dot product, you can distribute the scalar to either piece. And if you do the dot product of a vector with itself, it's just going to be the magnitude of that vector squared. So we're going to use those properties here a couple different times. So here I have a dot of a vector with itself. Here I have dot a vector with itself. Here I have scalars that I can use. So let's see what we've got. Remember that this all equals 0. So I've got 2 times the magnitude of a squared. Here I've got 4 times b dot a. Here I have a dot b. And here I have minus 2 times the magnitude of b squared. Nice thing is that some of those values are known. We know the magnitude of a is 2. We know the magnitude of b is square root of 5. So now we're really going to get somewhere. So I'm going to see if I can fit it in this little box here. We'll see. Might be a little ambitious. So magnitude of a is 2. So I have 2 times 2 squared. Here I have negative 4 times a number plus the same number. So I'm going to write that as negative 3 times b dot a. And then absolute value of b, the magnitude of b is square root of 5. So if you square that, you get 5. So minus 2 times 5 also has to equal 0. So, okay, 2 times 2 squared is 8. So we have 8 minus 3 b dot a minus 10 equals 0. So I guess that means that's a negative 2. So negative 3 b dot a minus 2 is 0. Negative 3 b dot a is 2. So b dot a is negative 2/3. Great. But we didn't actually care just about the value of the dot product. I mean, that was hard enough, but we got the value of the dot product. So now we're going to return back to the very first thing I wrote in this video, which is that the dot product is equal to the magnitudes times the cosine of the angle. So what I know now is that negative 2/3 is equal to 2 times square root of 5 cosine of theta. And so that means if I divide by 2, divide by the square root of 5, that means I have negative 1 over 3 root 5 is cosine theta. So we got to inverse cosine that and see what happens. I think it doesn't tell me about radians or degrees, so I don't think it really matters. I think I have my calculator. Well, it's sort of, I guess it's sort of typical in this class to do radians. So I'll just do it in radians. Okay, so here's what I got typed in. And that's what you get. 1.7. Okay. So by the way, I knew that it was going to be an obtuse angle. I want you to think about how I knew it was going to be an obtuse angle. And the reason is, as soon as I had cosine of theta equals a negative value, I knew I had to be in the second quadrant. I knew I had to be over 90 degrees. In other words, bigger than pi over 2. And so pi over 2 is about 1.5. So that makes sense that it'd have an answer of 1.72. So there you go. Basically, the purpose of this question is to have you go through the different properties of the scalar product and realize that a lot of the old algebra tricks that you knew how to do with just regular numbers also works when you're doing the scalar product with vectors. That's one of the nice things about the scalar product is it takes vectors and turns them into just regular numbers. Please let me know if something was confusing.